So this video is going to be looking at the chi-squared test. The chi-squared test can be used to analyse two bits of categorical data. This categorical data must be in the form of frequencies. It can't be in the form of percentages or proportions. It deems the association between the two sets. The chi-squared test, the formula is given as follows. It does look quite complicated now, however we'll break it down and it'll be a lot more simple by the end of the video. Constructing your chi-squared test. There are 5 steps to construct a successful chi-squared test. First of all, state a hypothesis. Second, construct contingency tables for both observed and expected values. 3. Apply the formula. 4. Determine the critical value for your test. 5. Conclude your test by failing to reject or rejecting the null hypothesis. Step 1. State your hypothesis. You need to create a null hypothesis and an alternative hypothesis. Your null hypothesis is always that there is no association between the two categories. Your alternative hypothesis is always that there is an association between the two categories. Step 2. Contingency tables. You need 2 contingency tables in order to form your chi-squared test statistic. One contingency table shows the observed values. This is just how many times a certain event happened in the experiment. The other shows all the expected values, which is given by this calculation here. So the expected values of the ith row jth column is equal to the row sum of the ith row multiplied by the column sum of the jth column. This is all divided by the total number in the population or the total number in the sample. Step 3. Apply the formula. So now we have our observed and expected values, we can carry out the calculation. Chi, that's just a Greek letter to which this test is signified by. The sigma notation just means that you're adding every term in the calculation. Our observed value in the ith jth column is denoted by Lij, and our expected value in the ith jth column is denoted by Eij. So it's observed value, take expected value, all squared, divided by expected value. Step 4. Determine the critical value. We need to do 2 things to determine the critical value. First of all, the degrees of freedom. So where m is the number of rows and n is the number of columns, the degrees of freedom can be obtained by the following calculation. So the number of rows minus 1, take the number of columns minus 1. The second thing that we need to do is the level of significance of our test. The level of significance is the small number given next to the chi-squared symbol in the 3rd row of this table. If for whatever reason your table is given in this form, that is simply 1 minus the percentage that you're testing to. Down the bottom here we've got the degrees of freedom. So degrees of freedom, test statistic, meet together, and that will be the number that you're looking for. Step 5. Draw your conclusions. From evaluating the critical value and our chi-squared statistic, we'll be able to do one of the following. Where the chi-squared statistic is less than the critical value, we failed to reject the null hypothesis. When the chi-square statistic is greater than the critical value, we reject the null hypothesis. This one in plain English is accepting the null hypothesis to be true. So let's have a look at a basic example. A random sample of 400 people in the centre of Didcot were classified according to their employment status, employed or unemployed, on the mode of transport, walk, bus or car, that they used most whilst travelling around the town. Step 1. State the hypothesis. So, the null hypothesis will be that there is no association between employment and how people travel around Didcot. H1. There is an association between employment and how people travel around Didcot. Our contingency tables are given as follows. So in this particular experiment, there was 160 people recorded who were employed and mainly travelled by car, for example. Our expected values need to be calculated. Notice the row sums and the column sums are all the same. So the expected value of the ith row, jth column is equal to the sum of the ith row multiply the sum of the jth column, all divided by the total number of people in our observed data, which in this case is 400. So applying this formula to the numbers that we have here, for example, in the employed and car category, there'll be 280 people. From there, times it by 210 people from there, and divided by 400, which is the total number given there. These will give you these nice numbers, and now we have all the information that we need to apply the formula. So now we've got these, the formula is given like this. So the observed value, take the expected value all squared over the expected value. For example, 160 minus 147, 13 all squared, 169. This is all divided by 169 divided by 147 will give us the value for that particular sum. Here we have all the sums for all the boxes. Notice how there's 6 observed values, 6 expected values, and also 6 things that need to be calculated. I'm going to plug this into the calculator. We're going to return a value of about 19.5, or 19.46 at 3 decimal place. Step 4. Determine the critical value. First of all, the degrees of freedom is given by the number of rows minus 1, the number of columns minus 1. So the number of rows, 2 take 1, 1, 3 take 1, 2. Multiply them together, you get 2. So we know that 2 is our degrees of freedom. We want the test to be at the 5% significance level. So we'll be looking at the 5% column just there. So reading across from 2 and down from the 5% column, the value of 5.991 will be returned. 5.991 will then be the critical value for our test. Step 5. Draw the conclusions. Recall that chi-squared, our chi-squared statistic was 19.46, and our critical value with 2 degrees of freedom at the 5% level was 5.99. These results satisfy that our chi-squared test statistic is greater than the critical value. Therefore, we reject the null hypothesis. This concludes that there is an association between employment status and how people travel around Didcot.